solar power is the conversion of sunlight into electricity either directly using photovoltaics, or indirectly using concentrated solar power. Concentrated solar power systems use lenses or mirrors and tracking systems to focus a large area of sunlight into a small beam. Photovoltaics convert light into electric current using the photovoltaic effect. Photovoltaics were initially, and still are, used to power small and medium-sized applications, from the calculator powered by a single solar cell to off-grid homes powered by a photovoltaic array. They are an important and relatively inexpensive source of electrical energy where grid power is inconvenient, unreasonably expensive to connect, or simply unavailable. However, as the cost of solar electricity is falling, solar power is also increasingly being used even in grid-connected situations as a way to feed low-carbon energy into the grid. Commercial concentrated solar power plants were first developed in the 1980s. The 392 MW Iseg CSP installation is the largest solar power plant in the world, located in the Mojave Desert of California. Other large CSP plants include the SEGS in the Mojave Desert of California, the Solnova Solar Power Station and the Andesol Solar Power Station, both in Spain. The 290 MW Agua Caliente Solar Project in the United States, and the 221 MW Sharanka Solar Park in India, are the World Unregistered Trademark S largest photovoltaic power stations. Concentrated solar power. Concentrating solar power systems use lenses or mirrors and tracking systems to focus a large area of sunlight into a small beam. The concentrated heat is then used as a heat source for a conventional power plant. A wide range of concentrating technologies exists, the most developed are the parabolic trough, the concentrating linear Fresnel reflector, the Stirling dish and the solar power tower. Various techniques are used to track the sun and focus light. In all of these systems a working fluid is heated by the concentrated sunlight, and is then used for power generation or energy storage. Thermal storage efficiently allows up to 24-hour electricity generation. A parabolic trough consists of a linear parabolic reflector that concentrates light onto a receiver positioned along the reflector's focal line. The receiver is a tube positioned right above the middle of the parabolic mirror and is filled with a working fluid. The reflector is made to follow the sun during daylight hours by tracking along a single axis. Parabolic trough systems provide the best land use factor of any solar technology. The SEGS plants in California and Axona's Nevada Solar One near Boulder City, Nevada are representatives of this technology. Compact linear Fresnel reflectors are CSP plants which use many thin mirror strips instead of parabolic mirrors to concentrate sunlight onto two tubes with working fluid. This has the advantage that flat mirrors can be used which are much cheaper than parabolic mirrors, and that more reflectors can be placed in the same amount of space, allowing more of the available sunlight to be used. Concentrating linear Fresnel reflectors can be used in either large or more compact plants. The Stirling solar dish combines a parabolic concentrating dish with a Stirling engine which normally drives an electric generator. The advantages of Stirling solar over photovoltaic cells are higher efficiency of converting sunlight into electricity and longer lifetime. Parabolic dish systems give the highest efficiency among CSP technologies. The 50 kilowatt Big Dish in Canberra, Australia is an example of this technology. A solar power tower uses an array of tracking reflectors to concentrate light on a central receiver atop a tower. Power towers are more cost-effective, offer higher efficiency and better energy storage capability among CSP technologies. The PS10 solar power plant and PS20 solar power plant are examples of this technology. Photovoltaics. A solar cell, or photovoltaic cell, is a device that converts light into electric current using the photovoltaic effect. The first solar cell was constructed by Charles Fritz in the 1880s. The German industrialist Ernst Werner von Siemens was among those who recognized the importance of this discovery. In 1931, the German engineer Bruno Lang developed a photocell using silver selenide in place of copper oxide, although the prototype selenium cells converted less than 1% of incident light into electricity. Following the work of Russell Ohl in the 1940s, Researchers Gerald Pearson, Calvin Fuller and Darrell Chapin created the silicon solar cell in 1954. These early solar cells cost $286 a USD watt and reached efficiencies of 4.5 a Euro 6%. Photovoltaic power systems. Solar cells produce direct current power which fluctuates with the sunlight's intensity. For practical use, this usually requires conversion to certain desired voltages or alternating current, through the use of inverters. Multiple solar cells are connected inside modules. Modules are wired together to form arrays, then tied to an inverter, which produces power at the desired voltage, and for AC, the desired frequency phase. Many residential systems are connected to the grid wherever available, especially in developed countries with large markets. In these grid-connected PV systems, use of energy storage is optional. In certain applications such as satellites, lighthouses, or in developing countries, batteries or additional power generators are often added as backups. Such standalone power systems permit operations at night and at other times of limited sunlight. Development and deployment. The early development of solar technology starting in the 1860s was driven by an expectation that coal would soon become scarce. However, development of solar technology stagnated in the early 20th century in the face of the increasing availability, economy, and utility of coal and petroleum. In 1974 it was estimated that only 6 private homes in all of North America were entirely heated or cooled by functional solar power systems. The 1973 oil embargo and 1979 energy crisis caused a reorganization of energy policies around the world and brought renewed attention to developing solar technologies. Deployment strategies focused on incentive programs such as the Federal Photovoltaic Utilization Program in the U.S. and the Sunshine Program in Japan. Other efforts included the formation of research facilities in the U.S., Japan, and Germany. Between 1970 and 1983 photovoltaic installations grew rapidly, but falling oil prices in the early 1980s moderated the growth of PV from 1984 to 1996. Since 1997, PV development has accelerated due to supply issues with oil and natural gas, global warming concerns, and the improving economic position of PV relative to other energy technologies. Photovoltaic production growth has averaged 40% per year since 2000 and worldwide installed capacity reached 139 GW at the end of 2013, with Germany having the most cumulative installations and Italy having the highest percentage of electricity generated by solar. As of October 2011, the largest photovoltaic power plants in the world are the Sarnia Photovoltaic Power Plant, Montalto di Castro Photovoltaic Power Station and Finsterwalder Solar Park. There are also many large plants under construction. The Desert Sunlight Solar Farm is a 550 MW solar power plant under construction in Riverside County, California, that will use thin-film solar photovoltaic modules made by First Solar. The Topaz Solar Farm is a 550 MW photovoltaic power plant, being built in San Luis Obispo County, California. The Blythe Solar Power Project is a 500 MW photovoltaic station under construction in Riverside County, California. The Aguacaliente Solar Problem is a 290 MW photovoltaic solar generating facility being built in Yuma County, Arizona. The California Valley Solar Ranch is a 250 MW solar photovoltaic power plant, which is being built by SunPower in the Carrizo Plain, northeast of California Valley. The 230 MW Antelope Valley Solar Ranch is a first solar photovoltaic project which is under construction in the Antelope Valley area of the western Mojave Desert, and due to be completed in 2013. At the end of September 2013, IKEA announced that solar panel packages for houses will be sold at 17 United Kingdom IKEA stores by the end of July 2014. The decision followed a successful pilot project at the Lakeside IKEA store, whereby one photovoltaic system was sold almost every day. The panels are manufactured by a Chinese company named Heinergy Holding Group Limited. Photovoltaic power stations. Concentrating solar thermal power. Commercial concentrating solar thermal power plants were first developed in the 1980s. The 370 MW Vanpur solar power facility, located in California's Mojave Desert, is the world unregistered trademark's largest solar thermal power plant project. Other large CSP plants include the Solnova Solar Power Station, the Andasol Solar Power Station, and Extrasol Solar Power Station, all in Spain. The principal advantage of CSP is the ability to efficiently add thermal storage, allowing the dispatching of electricity over up to a 24-hour period. Since peak electricity demand typically occurs at about 5 p.m., many CSP power plants use 3 to 5 hours of thermal storage. Economics. Photovoltaic systems use no fuel and modules typically last 25 to 40 years. The cost of installation is almost the only cost, as there is very little maintenance required. Installation cost is measured in dollar per watt or /watt. The electricity generated is sold for a cent per kilowatt-hour. 1 watt of installed photovoltaics generates roughly 1 to 2 kilowatt-hours a year, as a result of the local insolation. The product of the local cost of electricity and the insolation determines the break-even point for solar power. The International Conference on Solar Photovoltaic Investments, organized by EPIA, has estimated that PV systems will pay back their investors in 8 to 12 years. As a result, since 2006 it has been economical for investors to install photovoltaics for free in return for a long-term power purchase agreement. 50% of commercial systems were installed in this manner in 2007 and over 90% by 2009. As of 2011, the cost of PV has fallen well below that of nuclear power and is set to fall further. The average retail price of solar cells as monitored by the Solar Buzz Group fell from $3.50 per watt to $2.43 per watt over the course of 2011, and a decline to prices below $2 per watt seems inevitable. A U.S. study of the amount of economic installations agrees closely with the actual installations. For large-scale installations, prices below $1 per watt are now common. In some locations, PV has reached grid parity, the cost at which it is competitive with coal or gas-fired generation. More generally, it is now evident that, given a carbon price of $50 per ton, which would raise the price of coal-fired power by 5 carats per kilowatt-hour, solar PV will be cost-competitive in most locations. The declining price of PV has been reflected in rapidly growing installations, totaling about 23 GW in 2011. Although some consolidation is likely in 2012, as firms try to restore profitability, strong growth seems likely to continue for the rest of the decade. Already, by one estimate, total investment in renewables for 2011 exceeded investment in carbon-based electricity generation. Additionally, governments have created various financial incentives to encourage the use of solar power, such as feed-in tariff programs. Also, renewable portfolio standards impose a government mandate that utilities generate or require a certain percentage of renewable power regardless of increased energy procurement costs. In most states, RPS goals can be achieved by any combination of solar, wind, biomass, landfill gas, ocean, geothermal, municipal solid waste, hydroelectric, hydrogen, or fuel cell technologies. Xi Zhengrong has said that, as of 2012, unsubsidized solar power is already competitive with fossil fuels in India, Hawaii, Italy and Spain. He said we're at a tipping point. No longer are renewable power sources like solar and wind a luxury of the rich. They are now starting to compete in the real world without subsidies. Solar power will be able to compete without subsidies against conventional power sources in half the world by 2015 inches. Energy cost. The PV industry is beginning to adopt levelized cost of energy as the unit of cost. For a 10 MW plant in Phoenix, Arizona, the LCOE is estimated at 15 cents to 22 cents per kilowatt-hour in 2005. The table below illustrates the calculated total cost in U.S. cents per kilowatt-hour of electricity generated by a photovoltaic system as function of the investment cost and the efficiency, assuming some accounting parameters such as cost of capital and depreciation period. The row headings on the left show the total cost, per peak kilowatt, of a photovoltaic installation. The column headings across the top refer to the annual energy output in kilowatt-hours expected from each installed peak kilowatt. This varies by geographic region because the average insolation depends on the average cloudiness and the thickness of atmosphere traversed by the sunlight. It also depends on the path of the sun relative to the panel and the horizon. Panels can be mounted at an angle based on latitude, or solar tracking can be utilized to access even more perpendicular sunlight, thereby raising the total energy output. The calculated values in the table reflect the total cost in cents per kilowatt-hour produced. They assume a 5%/year total capital cost. Grid parity. Grid parity, the point at which the cost of photovoltaic electricity is equal to or cheaper than the price of grid power, is more easily achieved in areas with abundant sun and high costs for electricity such as in California and Japan. The fully loaded cost of solar electricity in 2008 was 25 cents per kilowatt-hour or less in most of the OECD countries. By late 2011, the fully loaded cost was predicted to fall below 15 cents per kilowatt-hour for most of the OECD and reach 10 cents per kilowatt-hour in sunnier regions. These cost levels are driving three emerging trends: vertical integration of the supply chain, origination of power purchase agreements by solar power companies, unexpected risk for traditional power generation companies, grid operators and wind turbine manufacturers. Grid parity was first reached in Spain in 2013, Hawaii and other islands that otherwise use fossil fuel to produce electricity, and most of the U.S. is expected to reach grid parity by 2015. General Electric's chief engineer predicted grid parity without subsidies in sunny parts of the United States by around 2015. Other companies predict an earlier date. The cost of solar power will be below grid parity for more than half of residential customers and 10% of commercial customers in the OECD, as long as grid electricity prices do not decrease through 2010. Self-consumption. In cases of self-consumption of the solar energy, the payback time is calculated based on how much electricity is not purchased from the grid. For example, in Germany, with electricity prices of €0.25 per kWh and insolation of 900 kWh/kW, 1 kWp will save €225 per year, and with an installation cost of €1,700 per kWp, the system cost will be returned in less than 7 years. However, in many cases, the patterns of generation and consumption do not coincide, and some or all of the energy is fed back into the grid. The electricity is sold, and at other times when energy is taken from the grid, electricity is bought. The relative costs and prices obtained affect the economics. Energy pricing and incentives. The political purpose of incentive policies for PV is to facilitate an initial small-scale deployment to begin to grow the industry, even where the cost of PV is significantly above grid parity, to allow the industry to achieve the economies of scale necessary to reach grid parity. The policies are implemented to promote national energy independence, high-tech job creation and reduction of CO2 emissions. 3 incentive mechanisms are used: investment subsidies, the authorities refund part of the cost of installation of the system; feed-in tariffs, the electricity utility buys PV electricity from the producer under a multi-year contract at a guaranteed rate. Solar renewable energy certificates, rebates. With investment subsidies, the financial burden falls upon the taxpayer, while with feed-in tariffs the extra cost is distributed across the utility's customer bases. While the investment subsidy may be simpler to administer, the main argument in favor of feed-in tariffs is the encouragement of quality. Investment subsidies are paid out as a function of the nameplate capacity of the installed system and are independent of its actual power yield over time, thus rewarding the overstatement of power and tolerating poor durability and maintenance. Some electric companies offer rebates to their customers, such as Austin Energy in Texas, which offers $2.50 per watt installed up to $15,000. Net metering. In net metering, the price of the electricity produced is the same as the price supplied to the consumer, and the consumer is billed on the difference between production and consumption. Net metering can usually be done with no changes to standard electricity meters, which accurately measure power in both directions and automatically report the difference, and because it allows homeowners and businesses to generate electricity at a different time from consumption, effectively using the grid as a giant storage battery. With net metering, deficits are billed each month while surpluses are rolled over to the following month. Best practices call for perpetual rollover of kilowatt-hour credits. Excess credits upon termination of service are either lost, or paid for at a rate ranging from wholesale to retail rate or above, as can be excess annual credits. In New Jersey, annual excess credits are paid at the wholesale rate, as are leftover credits when a customer terminates service. Feed-in tariffs. With feed-in tariffs, the financial burden falls upon the consumer. They reward the number of kilowatt-hours produced over a long period of time, but because the rate is set by the authorities, it may result in perceived overpayment. The price paid per kilowatt-hour under a feed-in tariff exceeds the price of grid electricity. Net metering refers to the case where the price paid by the utility is the same as the price charged. Solar renewable energy credits, alternatively, SRECs allow for a market mechanism to set the price of the solar-generated electricity subsidy. In this mechanism, a renewable energy production or consumption target is set, and the utility is obliged to purchase renewable energy or face a fine. The producer is credited for an SREC for every 1,000 kilowatt-hours of electricity produced. If the utility buys this SREC and retires it, they avoid paying the ACP. In principle, this system delivers the cheapest renewable energy, since the all-solar facilities are eligible and can be installed in the most economic locations. Uncertainties about the future value of SRECs have led to long-term SREC contract markets to give clarity to their prices and allow solar developers to pre-sell hedge their SRECs. Financial incentives for photovoltaics differ across countries, including Australia, China, Germany, Israel, Japan, and the United States, and even across states within the U.S. The Japanese government, through its Ministry of International Trade and Industry, ran a successful program of subsidies from 1994 to 2003. By the end of 2004, Japan led the world in installed PV capacity with over 1.1 GW. In 2004, the German government introduced the first large-scale feed-in tariff system, under a law known as the EEG, which resulted in explosive growth of PV installations in Germany. At the outset, the FIT was over 3x the retail price or 8x the industrial price. The principle behind the German system is a 20-year flat-rate contract. The value of new contracts is programmed to decrease each year, in order to encourage the industry to pass on lower costs to the end users. The program has been more successful than expected, with over 1 GW installed in 2006, and political pressure is mounting to decrease the tariff to lessen the future burden on consumers. Subsequently, Spain, Italy, Greece and France introduced feed-in tariffs. None have replicated the programmed decrease of FIT in new contracts though, making the German incentive relatively less and less attractive compared to other countries. The French and Greek FIT offer a high premium for building integrated systems. California, Greece, France and Italy have 30 to 50% more insulation than Germany, making them financially more attractive. The Greek domestic solar roof program has internal rates of return of 10 to 15% at current commercial installation costs, which, furthermore, is tax-free. In 2006, California approved the California Solar Initiative, offering a choice of investment subsidies or FIT for small and medium systems and FIT for large systems. The small system FIT of 39 cents per kilowatt-hour expires in just 5 years, and the alternate EPBB residential investment incentive is modest, averaging perhaps 20% of cost. All California incentives are scheduled to decrease in the future depending as a function of the amount of PV capacity installed. At the end of 2006, the Ontario Power Authority began its Standard Offer program, the first in North America for small renewable projects. This guarantees a fixed price of 42 cents per kilowatt-hour over a period of 20 years. Unlike net metering, all the electricity produced is sold to the OPA at the SOP rate. The generator then purchases any needed electricity at the current prevailing rate. The difference should cover all the costs of installation and operation over the life of the contract. On October 1, 2009, OPA issued a feed-in tariff program, increasing this fixed price to $0.802 per kilowatt-hour. The price per kilowatt-hour or per peak kilowatt of the FIT or investment subsidies is only one of three factors that stimulate the installation of PV. The other two factors are insulation and administrative ease of obtaining permits and contracts. Unfortunately, the complexity of approvals in California, Spain and Italy has prevented comparable growth to Germany even though the return on investment is better. In some countries, additional incentives are offered for BIPV compared to standalone PV. France plus 0.16 European euros per kilowatt-hour or plus 0.27 European euros per kilowatt-hour, Italy plus 0.04 European euros to 0.09 European euros kWh, Germany plus 0.05 European euros per kilowatt-hour. Environmental impacts. Unlike fossil fuel-based technologies, solar power does not lead to any harmful emissions during operation, but the production of the panels leads to some amount of pollution. Greenhouse gases. The life cycle greenhouse gas emissions of solar power are in the range of 22 to 46 gram per kilowatt-hour depending on if solar thermal or solar PV is being analyzed, respectively. With this potentially being decreased to 15 gram per kilowatt-hour in the future. For comparison, a combined cycle gas-fired power plant emits some 400-599 gram per kilowatt-hour, an oil-fired power plant 893 gram per kilowatt-hour, a coal-fired power plant 915-994 gram per kilowatt-hour, or with carbon capture and storage some 200 gram per kilowatt-hour, and a geothermal high-temp power plant 91-122 gram per kilowatt-hour. The life cycle emission intensity of hydro, wind and nuclear power are lower than solar's as of 2011 as published by the IPCC, and discussed in the article Life Cycle Greenhouse Gas Emissions of Energy Sources. Similar to all energy sources where their total life cycle emissions primarily lay in the construction and transportation phase, the switch to low-carbon power in the manufacturing and transportation of solar devices would further reduce carbon emissions. BP Solar owns two factories built by SolarX in which all of the energy used to manufacture solar panels is produced by solar panels. A 1 kilowatt system eliminates the burning of approximately 170 pounds of coal, 300 pounds of carbon dioxide from being released into the atmosphere, and saves up to 105 gallons of water consumption monthly. Energy payback. The energy payback time of a power generating system is the time required to generate as much energy as was consumed during production of the system. In 2000 the energy payback time of PV systems was estimated as 8 to 11 years, and in 2006 this was estimated to be 1.5 to 3.5 years for crystalline silicon PV systems and 1-1.5 years for thin film technologies. Another economic measure, closely related to the energy payback time, is the energy returned on energy invested or energy return on investment, which is the ratio of electricity generated divided by the energy required to build and maintain the equipment, which varies according to local energy prices, subsidies available and metering techniques. With lifetimes of at least 30 years, the EROEI of PV systems are in the range of 10 to 30, thus generating enough energy over their lifetimes to reproduce themselves many times depending on what type of material, balance of system, and the geographic location of the system. Cadmium. One issue that has often raised concerns is the use of cadmium in cadmium telluride solar cells. Cadmium in its metallic form is a toxic substance that has the tendency to accumulate in ecological food chains. The amount of cadmium used in thin-film PV modules is relatively small, and with proper emission control techniques in place the cadmium emissions from module production can be almost zero. Current PV technologies lead to cadmium emissions of 0.3 to 0.9 microgram per kilowatt-hour over the whole life cycle. Most of these emissions actually arise through the use of coal power for the manufacturing of the modules, and coal and lignite combustion leads to much higher emissions of cadmium. Life cycle cadmium emissions from coal is 3.1 microgram per kilowatt-hour, lignite 6.2, and natural gas 0.2 microgram per kilowatt-hour. Note that if electricity produced by photovoltaic panels were used to manufacture the modules instead of electricity from burning coal, cadmium emissions from coal power usage in the manufacturing process could be entirely eliminated. Energy storage methods. Solar energy is not available at night, making energy storage an important issue in order to provide the continuous availability of energy. Both wind power and solar power are intermittent energy sources, meaning that all available output must be taken when it is available and either stored for when it can be used, or transported, over transmission lines, to where it can be used. Off-grid PV systems have traditionally used rechargeable batteries to store excess electricity. With grid-tied systems, excess electricity can be sent to the transmission grid. Net metering and feed-in tariff programs give these systems a credit for the electricity they produce. This credit offsets electricity provided from the grid when the system cannot meet demand, effectively using the grid as a storage mechanism. Credits are normally rolled over from month to month and any remaining surplus settled annually. When wind and solar are a small fraction of the grid power, other generation techniques can adjust their output appropriately, but as these forms of variable power grow, this becomes less practical. Solar energy can be stored at high temperatures using molten salts. Salts are an effective storage medium because they are low cost, have a high specific heat capacity and can deliver heat at temperatures compatible with conventional power systems. The Solar 2 used this method of energy storage, allowing it to store 1.44 TJ in its 68 m3 storage tank, enough to provide full output for close to 39 hours, with an efficiency of about 99%. Conventional hydroelectricity works very well in conjunction with intermittent electricity sources such as solar and wind. The water can be held back and allowed to flow as required with virtually no energy loss. Where a suitable river is not available, pumped storage hydroelectricity stores energy in the form of water pumped when surplus electricity is available, from a lower elevation reservoir to a higher elevation one. The energy is recovered when demand is high by releasing the water, the pump becomes a turbine, and the motor a hydroelectric power generator. However, this loses some of the energy to pumpage losses. Artificial photosynthesis involves the use of nanotechnology to store solar electromagnetic energy in chemical bonds, by splitting water to produce hydrogen fuel or then combining with carbon dioxide to make biopolymers such as methanol. Many large national and regional research projects on artificial photosynthesis are now trying to develop techniques integrating improved light capture, quantum coherence methods of electron transfer and cheap catalytic materials that operate under a variety of atmospheric conditions. Senior researchers in the field have made the public policy case for a global project on artificial photosynthesis to address critical energy security and environmental sustainability issues. Wind power and solar power tend to be somewhat complementary, as there tends to be more wind in the winter and more sun in the summer, but on days with no sun and no wind the difference needs to be made up in some manner. Solar power is seasonal, particularly in northern southern climates, away from the equator, suggesting a need for long-term seasonal storage in a medium such as hydrogen. The storage requirements vary and in some cases can be met with biomass. The Institute for Solar Energy Supply Technology of the University of Kassel pilot tested a combined power plant linking solar, wind, biogas and hydro storage to provide load-following power around the clock, entirely from renewable sources. Experimental solar power. Concentrated photovoltaic systems employ sunlight concentrated onto photovoltaic surfaces for the purpose of electrical power production. Solar concentrators of all varieties may be used, and these are often mounted on a solar tracker in order to keep the focal point upon the sun as the sun moves across the sky. Luminescent solar concentrators can also be regarded as a CPV system. Concentrated photovoltaics are useful as they can improve efficiency of PV solar panels drastically. Thermoelectric, or thermovoltaic devices convert a temperature difference between dissimilar materials into an electric current. first proposed as a method to store solar energy by solar pioneer much out in the 1800s, thermoelectrics re-emerged in the Soviet Union during the 1930s. Under the direction of Soviet scientist Abramovich, a concentrating system was used to thermoelectrically generate power for a 1 HP engine. The mogenerators, but in the following cases powered by the heat source plutonium-238 and radioisotope thermoelectric generators, are used in the U.S. space program as an energy conversion technology for powering deep space missions such as the Mars Curiosity rover, Cassini, Galileo and Viking. Research in this area of the mogenerators, which can use any heat source, is focused on raising the efficiency of these devices from 7–8% to 15–20%. Physicists have claimed that recent technological developments bring the cost of solar energy more in parity with that of fossil fuels. In 2007, David Feynman, the director of the Ben-Gurion National Solar Energy Center of Israel, announced that the center had entered into a project with Zenith Solar to create a home solar energy system that uses a 10-square-meter reflector dish. In testing, the concentrated solar technology proved to be up to 5 times more cost-effective than standard flat photovoltaic silicon panels, which would make it almost the same cost as oil and natural gas. A prototype ready for commercialization achieved a concentration of solar energy that was more than 1,000 times greater than standard flat panels. See also. References. Sources. Further reading: Smaller, Cheaper, Faster, Does Maria Unregistered Trademark S Law Apply to Solar Cells? Scientific American Analyses.